So far we have learned how to amplify, attenuate, and invert a signal. In this lesson we will learn configurations that will allow us to perform operations like addition and subtraction. In the diagram you can see the basic configuration of an adder. If you observe it carefully, you will notice that it looks like an inverting amplifier but with more resistors at the input. The circuit is indeed an inverting amplifier, but thanks to the behavior of the circuit, it can be used to add voltages. And because it is an inverting amplifier, the output is expected to change sign. We will analyze the circuit in order to understand how it works. Since the circuit has multiple voltage sources, we can use superposition to analyze it. If you notice, the positive pin of the op-amp is connected to ground. Therefore, we can use the concept of virtual ground to simplify the analysis. Let's start with superposition and make the voltage sources V2 and V3 0 volts. If you remember the superposition lesson, when a voltage source is 0 volts, it behaves as it is a short circuit. In this case, the resistors R2 and R3 are connected to ground. The other extreme of the resistor is connected to the virtual ground. Since both of the terminals of the resistors have the same voltage, which in this case is 0 volts, no current flows through them. So the currents IR2 and IR3 are 0. This simplifies the equation of the negative pin of the op-amp. Since there is no current IR2 and IR3, this circuit is reduced to an inverting amplifier with a single input. We can define the equation for the node as IR1 equal to IRF1. After replacing the currents by the voltages using Ohm's law and solving for Vout, we obtain the formula of the inverting amplifier. Repeating the analysis for the other sources will lead to similar results, because for each source, the circuit is reduced to an inverting amplifier. Knowing that, we can combine the contributions of all sources and obtain the final solution using superposition. We can see that the output is the sum of all voltages. It is important to notice that we can control the scaling of each voltage by changing the value of the corresponding resistor. Here we can see two particular cases. If we make all the resistors R1, R2, R3, and RF1 the same value, each voltage will have a scaling of 1. Therefore, the output will be the sum of the individual voltages. If we make RF1 3 times larger than the resistors R1 to R3, we will get as output the average voltage of the 3 inputs. We can scale every voltage according to the application needs. In this case, we analyze an adder with 3 inputs. But what if we need to add more than 3 voltages? Extending the circuit is very easy. If we need an extra input, we can simply add another resistor for the extra input. Thanks to the superposition, we can extend the formula adding terms for every new input that is added. Now let's make a first attempt to subtract voltages. If you remember the op-amp equation, you'll recall that there is an inherent subtraction operation. The op-amp subtracts the voltage at the negative pin from the voltage at the positive pin. We can obtain an initial version of a subtraction by combining the non-inverting amplifier with the inverting amplifier. The combination results in the following circuit. You can see that there is a voltage source V2 that corresponds to the inverting amplifier input. The voltage source V1 corresponds to the non-inverting amplifier. If we use superposition to analyze this circuit, we can see that by setting V1 to 0, the circuit becomes the inverting amplifier. On the other hand, setting V2 to 0, the circuit becomes the non-inverting amplifier. We do not need to analyze the circuit since we already know the formulas for the non-inverting and inverting configurations. We can obtain the final formula by combining the contributions of the two sources using superposition. That results in the following formula. We can see that the voltages V1 and V2 are subtracted, but they are scaled. Let's put some numeric values to see how the circuit behaves. If we make both resistors 1 kilo ohm, the scaling of the voltage V2 becomes 1. However, for the voltage V1, the scaling is 2. With this circuit, we cannot perform an actual subtraction, and by looking at the formula, we can conclude that it is not possible to pick a combination of values for R1 and RF that results in a subtraction. The only way of fixing the problem will be to scale the voltage V1 by 0.5 before it enters the op-amp. Scaling down V1 is very easy by using a voltage divider. Since the middle of the voltage divider is connected to the op-amp, we know that the current is practically zero. It is safe to assume that the op-amp will not disturb the voltage divider. From this circuit, we can obtain the following general formula. The main difference with the previous formula is that the voltage V1 now has two scaling factors. The new one is the voltage divider formula, which we know that is R3 over R3 plus R2. If we make all the resistors the same value, for example 1 kilo ohm, the gain of the voltage divider is 1/2 or 0.5. That is multiplied by 2 times V1, which becomes 1. And then it subtracts V2. After simplification, the formula results in V1 minus V2. This op-amp configuration is one of the most flexible. In this case, we use it as a subtraction, but it can be used for other operations that we will see in the subsequent lesson. I recommend you to remember this formula, or at least the process we used to obtain it. Here are the simulation results of the subtraction operation. In the top, we can see the voltage V1, which is a sine wave of 1 volt of amplitude. The voltage V2 is a constant 1 volt. In the bottom, we can see the result, which is the sine wave with an offset of -1 volt. To summarize this lesson, we learned that we can turn the inverting amplifier into an inverting adder. The adder can be easily expanded by adding more resistors, and we can easily derive the formula by using superposition. If we combine the inverting and non-inverting amplifiers, we can obtain a subtraction. But we need to adjust the gain of the positive voltage by adding a voltage divider. The resulting configuration is a very flexible configuration that can be used for many different operations.